Welcome, everyone. I'm thrilled that everyone is here to join us today for the Eclypsium webinar, Firmware Enumeration with Open Source Tools, or How Well Do You Know Your Device? My name is Melissa Russell, and I'll be the moderator for today's session, and just wanted to go over a couple of housekeeping items before we get started. Yes, the webinar is being recorded, and after the webinar concludes, we will be sending out links to both the webinar recording as well as the slides. We will be taking Q&A. We will have some pauses during the presentation to address some questions that might be very specific to certain sections, so don't hesitate to put your questions into the Q&A. And anything that we miss, we will make sure to follow up with afterwards. So at this time, I'd like to go ahead and introduce our speaker. Our speaker is Paul Asadoorian, and he is currently our Firmware Security Evangelist here at Eclypsium. He was also the founder of Security Weekly, which is a security podcast network. It was acquired by Cyber Risk Alliance back in 2020, and he now serves as a podcast host for Paul Security Weekly. At this time, Paul, I'd like to go ahead and turn it over to you. You have the floor.
Thank you so much, Melissa. Thanks, everyone, for joining today. As Melissa said, I am Paul Asadoorian. Currently, I am the Firmware Security Evangelist for Eclypsium. I joined Eclypsium in June of this year and have been doing a lot of work with the team and the community to highlight areas of firmware security or insecurity, as it were, in our field, and present to you today talking about open source tools for firmware enumeration. So it's my job to get our message and the message of firmware security out to the security community as a whole. So I've only been doing that since June. So if I don't have the answer to your question, I'm not shy saying I don't know, and I will get you an answer. A lot of this presentation and some of the blog posts that I've done recently, I've relied heavily on our research team to answer my questions to dig into some of these areas. So this is kind of the culmination of a 3-part blog post series. The third part has not yet been published, and you'll see some of that content towards the end. I am still working on part 3 of what I call my firmware realizations blog post series. And it really, that realizations blog post series is centered around this question. And I don't think it's a question that I was really asking of myself when, before I joined Eclypsium. But when I started looking into what we do and where firmware lives inside of our respective devices, I started asking, well, like, how many devices are inside of my device? I have a background in analyzing firmware and analyzing the security of firmware. And it was even astonishing to me just how many different areas within my own laptop, for example, that existed other devices that existed inside of it that also had firmware. And, I joke with John Lucades, who's our senior VP here at Eclypsium. I said, when he came to me, I knew that like firmware was really bad in terms of security. And now I'm realizing more and more that there's a lot more firmware than I realized inside of our computers. And so when you start analyzing and picking apart, there's of course all of these different areas. And I think the thing that's interesting to me about firmware is the threat landscape. But if you really think about the threat landscape and why firmware can be problematic, it's that firmware is just software that's inconvenient to program. And I love that quote, and I like to use it especially on this slide that highlights some of the areas where you'll find firmware inside of your computer. Now we're going to be digging into a couple of these areas today. I think that the 3 big areas of realization for me in terms of where I was finding the most problems in speaking with people here at Eclypsium, speaking to my friends in the community, and using these open source tools and methods in addition to Eclypsium's product to enumerate the firmware and discover any kind of issues or vulnerabilities in it. And that is the 3 main areas that I think I can pull on there are the first with secure boot, the second with Intel ME or CSME as they call it. And the final one is with BIOS write protections. Now, BIOS write protections will be the subject of the final part of my 3-part blog post series, and you'll see some of that content again towards the end. And not only are these areas for vulnerabilities to exist within our respective computing devices, they also carry with it a lot of attacks that have happened in the past. Not only have known firmware vulnerabilities increased over time, but also we've seen very specific threats and malware and threat actors going after some of these very specific areas. You can see there's some CVEs associated with CSME, Converged Security and Manageability Engine, I believe is where Intel now lands in how they're naming what we typically refer to as Intel ME or Management Engine. They now call it the Manageability Engine. They can't really make up their mind on what they want to call it, but today it's CSME. There are some CVEs, associated with those that in the blog post I'll dig into. You can read about how I've dug into some of those. You'll see how to find some of those vulnerabilities in this presentation as well. UEFI, of course, and a lot of the threats against UEFI are pretty prevalent today. We've seen some recent examples in the news recently about attackers specifically attacking UEFI, and of course, over time, attacking some of the other components inside of your computer at the firmware level. And I think the first thing to talk about defense, right, because this presentation really isn't about dissecting some of the attacks, but looking at some of the defenses and starting to look at your own devices for firmware conditions and or vulnerabilities. The first step is to check what version your BIOS or UEFI software is running on your system. And I think step one, for a number of reasons, is to make sure that you're on the latest version of your BIOS inside of your computer. Now, one of those reasons is if you're going to apply updates to your management engine, Intel ME, advice from manufacturers that I've observed always recommend you update your BIOS first. In a recent update from Microsoft in KB 5012170, which updates the revocation list for secure boot, and we'll cover that as we go through this presentation. There is also recommendation that in order to avoid some of the errors and mishaps that have happened with that update, to make sure that you update your BIOS to the latest revision. So it's important for a lot of reasons. It's a very fundamental thing. It may not be something that you think about every day, but for Linux systems, there's a really easy way using the dmidecode command to check your current BIOS version. So there's actually two different commands that I've been using to check my systems that are primarily Linux. You can do this on other platforms as well. The links in the lower left-hand corner will give you some examples on how to do this on your Mac systems or on your Windows systems as well. There's a few different ways to do it. However, I will focus a lot more on Linux as there's a lot more open source and built-in utilities on Linux systems to enumerate your firmware. And this, again, is the first step. So using dmidecode, it interfaces with the lower level hardware and software on your device and gives you your BIOS version and then also your BIOS release date. Now, from this step, it's a kind of a manual process to know if your BIOS is out of date or not, right? This gives you currently what it's running. You will have to then visit the manufacturer's website to see if you're actually on the latest version of your BIOS. But this is a good first step. See what version you're on, then go to your manufacturer's website, support page typically, and see if there are updates to it. Sometimes there is, sometimes there's not. My laptop happens to be from MSI, and they have not provided a BIOS update in some time, and your mileage is going to vary depending on which hardware manufacturer is responsible for the BIOS on your particular computer. So there's the first step in Linux, how to check your BIOS or UEFI version. Another great facility, and this is specific to Linux, and I will not very often, but sometimes cover ways to do this in Windows and other operating systems as well. But in Linux, again, which is the focus of this presentation, LVFS is a great project that was created by Richard Hughes. It's an open source project whose goal is to allow Linux users to enumerate which devices you have inside of your computer, determine if those devices have firmware, and then determine if there's an update to that firmware inside of your device. Now, with this project that's called the Linux Vendor Firmware Service, the vendors also have are can participate in this service. So if I'm a vendor and I make the Thunderbolt host controller as an example, I would have to go to the Linux Vendor Firmware Service. I would have to work with them, create an account, and start pushing firmware updates into the system that could then, by a Linux user, be applied to the firmware running inside of my computer. And there's a process, and you can go to fwupd.org, which is the homepage for LVFS, and you can see instructions from a user level. You can also see which vendors are working with the project and which state each of those vendors are in. Some of them are in a testing phase. Some of them are in a full-blown production phase where they're getting updates. I think Lenovo is pretty well established in LVFS, whereas some vendors like System 76 are still testing, but are in fact listed as working with this open source project. So if you're on Linux, use your distributions mechanism for installing software. fwupd, I believe, is the name of the package on most Linux systems that you would install. From there, you can run the command fwupd manager get-updates. That will list the available devices on your system and tell you if there are updates. Now, I do have to say that most of the time when I run this on my systems and my personal systems that I use every day, and also Linux systems that I manage, that there's not been too many instances of there being an update available, likely because these vendors have not, participated in the LVFS project yet. So I hope this project grows, as I think they are doing a great job of enabling, in this case, Linux users to enumerate things on your computing devices that have to do with firmware. Now, one of the things that you can see, if I go back to the previous slide, is the third bullet down, UEFI DBX. DBX is the revocation list for secure boot. It contains certificates and hashes of software that should not be loaded during the secure boot process. So if you've got secure boot enabled on your laptop or computer and you're trying to load software that has an entry in the DBX, secure boot should not load that software and should halt the boot process. And I'll talk at length about the different aspects of secure boot as well. And one of the first things that I observed in some of my computers was that my DBX was out of date. And I was like, well, how do I know if it's out of date? Other than using Eclypsium's product, which I'll show you some screenshots towards the end. I will focus, 90% of the time on ways to do this with open source software. But the product said, hey, your DBX is out of date. And then I started using other tools and go, well, how do I know if my revocation list for secure boot is out of date? And I wanted to find a way for folks to do this on their own and enumerate this on Linux systems. So if you run fwupdate manager get-devices, it will list out all of the available devices that it can find on your computer and a whole bunch of information about each of those devices. One of those is the version number of the particular firmware update in LVFS. And you can see here in the screenshot in the upper left, the current version is 77. Now, Richard Hughes has made posts and really wants to support updating the DBX on systems that are running LVFS. And in fact, if I run this command and I see I'm running version 77, if I visit fwupd.org and I go to the DBX update entry in LVFS, you'll see a number of different versions on that website, one of them being the latest version, which happens to be 217 being the latest version. I'm on version 77. So if I go through this exercise, I should realize that my DBX is out of date. Now you can see the DBX was updated most recently, thanks to our researchers, Mickey and Jesse, who presented at DEF CON Security Conference this year and uncovered vulnerabilities in select bootloaders that triggered an update to the revocation list, as those vulnerabilities have basically triggered the bootloaders to be included in the DBX, or at least a hash of those particular bootloaders. So there is a recent update, and my system here is out of date. So I want to just talk a little bit more about the secure boot certificate hierarchy, because it if you're going like I was to do this research on your own, it can be a little daunting to understand how all of this works. There are some confusing points. So basically, this is a root of trust that is created for secure boot enabled computers. It starts with the platform manufacturer, who will define a platform key. And when you look at the monikers of PK, KEK, DB, and DBX, keep in mind that these are the names of the variables in UEFI that can contain data, right? So one of the things that can be confusing is you look at the KEK, or the key exchange key, and you're like, well, that should just be one key, but it can actually be multiple. So these are variable stores that store the platform key, the key exchange key, which the key exchange keys are used to modify and or validate entries in the DB or DBX, because you wouldn't want an attacker to be able to just update your DB, which contains a list of authorized software, certificates and hashes of authorized software for the secure boot process, and the DBX are certificates and hashes of software that should not.
Paul, it seems like your audio cut out.
Sorry, I hit the mute on my microphone because I was moving around. I was talking about the key exchange key being used to validate the two databases, right? The DB, which are certificates and hashes of authorized software in the secure boot process, and the DBX, which are revoked certificates and hashes of revoked software in the secure boot process. And the key hierarchy that's described here is so attackers can't modify that. So not just anyone can go in and stick an entry in the DB. That would defeat the whole purpose of secure boot. So just a little more information about the hierarchy to reiterate. Typically, your computer comes with a platform key, or PK. It's typically a single platform vendor certificate. And you'll see, I'll show you how to enumerate these on your computers. When I look at my platform key was issued by ASUS. The key exchange keys, again, are used to maintain and update the DB and DBX and implement the DB and DBX checking. The key exchange keys, there can be multiple. And you'll see on my system, I actually had multiple key exchange keys. Then, of course, you have the authorized database of hashes and the forbidden database, right? So those can be certificates or hashes. And you see the graphic here really kind of helps you. Like there's a single platform key, multiple key exchange keys, and multiple entries in the DB and DBX, which do have finite storage limitations. I believe DB and DBX are 32 kilobytes maximum, but that can vary. So one of the first things as well to just talk quickly about previous research from Eclypsium and how you can check your systems. In 2020, Mickey and Jesse discovered that there were vulnerabilities in the Grub bootloader. And since there were vulnerabilities in the Grub bootloader that was installed on systems and had authorized entries in the DB, now these vulnerable Grub bootloaders have to be, their hashes and or certificates have to be put into the DBX. Eclypsium's GitHub page does contain a tool called Boothole detection that will check for this specific problem. So if you're worried that you might be running a Grub bootloader that contains a vulnerability that shouldn't be used in the secure boot process, you can run this script. On our GitHub page, you can also find, I believe, a PowerShell. There is a Windows version of this script as well. And it'll do some checks. It checks to see, using the mock-util, if secure boot is enabled or disabled. I'll show you a couple of other different ways to do that as well. And it tells you that if your Grub and or shim, which that's like a whole other presentation. Shim is also a software that's in the boot process for Linux systems and specifically exists so that secure boot can validate shim rather than 8 million versions of different bootloaders across all the Linux distributions. So this system scan clean for that. So there's one way, and this is freely available on our GitHub page, and there's also a link to the original research that we captured in our blog post. Okay, so the first question you might ask, now that you have a little bit of understanding of how secure boot works, is secure boot enabled on my system? And on Linux systems, you can use the firmware testing toolkit, which you can install on most Linux distributions. And with those command line switches, basically grep out the entries that indicate whether secure boot is enabled or not. So that's one way. If you have mockutil installed on your Linux system, --sb-state will indicate the status of secure boot and whether it is enabled or disabled. You can also do this in Windows PowerShell as well. And those PowerShell commands will give you the status of secure boot on your system as well. At the lower left-hand corner, I list some references and other ways, such as on Apple systems, as how you can tell or determine if secure boot is enabled. It's very different. It's a graphical interface described in that support article, and some of the references for the commands that are shown on this screen as well. Okay, so now that we know whether secure boot is enabled on our systems or not, I want to go through an exercise and understand what's in the variables on my system, right? Because this is going to differ from system to system. What are in the PK and KEK variables on my system? You can actually read this. In fact, if you use the commands that I outline on this slide, you can read the contents of these variables and enumerate the certificates, which certificates, who's been issued those certificates that exist on your system. And this is important when we get to how to update the DBX on your system, which is where this section will ultimately end. So the first thing you want to do is use EFI readvar, then tell it to read the PK and KEK variables and read those into a file. You're then going to convert that file into I believe SIG list asserts converts that into a DER format. That then you can run the OpenSSL commands on this page and convert that out into text. So that's how you read what's in the variables, convert it out into a certificate that's human readable, so you can then use the commands on this slide and see who the issuer was of each of those certificates. So these three certificates that I'm showing on this slide are the KEK, the three certificates that were stored in the KEK variable on one of my systems. One of my systems happens to be from ASUS, so my the key exchange key, one of them was from ASUS, from my motherboard manufacturer. One was issued by Microsoft, which is their third-party root certificate. So if you're not Microsoft and you want to get software validated for participation in secure boot, you issue that software and fill out and do a thing with Microsoft, essentially, that there's not too much documentation exactly how that works. You go to Microsoft, they then grant you the rights to run software in the secure boot process and be part of their third-party CA system. So that certificate is in there, as well as a certificate from Canonical, so that Linux systems can participate in secure boot. Canonical also has a certificate in the KEK. Okay, now the reason why all of that is important is I had to make sure all of that was in place. I had to understand whether secure boot was enabled or not on my system. I understood that my DBX was in fact out of date. I then said, if I were to take a DBX update from UEFI itself that is signed by and authorized by Microsoft's key exchange key as an example, I should be able to apply that to my system. And this was the question I had for our researchers. And I was like, can I do this without breaking anything, right? Like, secure boot's not enabled on my system. I need a DBX update. My KEK variable contains these certificates. Therefore, I can go to the uefi.org website. I can download a DBX update, which contains all of the certificates and hashes of software that has been revoked from the secure boot process. And lo and behold, it worked. So this is how you can manually, on a Linux system, update your DBX. Now, please do exercise caution. I did not go into any elaborate testing on here, but this is the process that I followed to read my existing, take a backup of my DBX, which again is just another variable that I can read using the EFI readvar command. I use the dbxtool to read that file and I can see there's 240 entries in there. I then went to the uefi.org website, got the latest DBX update file. I copied that to a specific location. I used an internal utility called sbkeysync. This was on my Ubuntu 20.04 system. And I stole that command from the systemd startup and ran that command. I read in the new DBX. So I'm sorry, that previous command sbkeysync is what actually applies my new DBX update. I then read my new DBX update, and now I see that I have 271 entries. And as far as I understand, it will actually do a merge of everything. So it'll merge the existing and new files, providing me with an updated DBX. And all of these commands in this process is documented in my blog post that I link to on the slide. So that was like my first kind of foray into secure boot and how I would manage it on my systems. So some advice is to update firmware. As I said, a lot of these updates for the secure boot process and other firmware within your system, in this case, specifically secure boot, may come from your operating system manufacturer. It may come from the manufacturer of your motherboard. They're all part of the supply chain that can potentially help you update your keys and or revocation or DBs on your system for secure boot. Microsoft, for example, especially on the Surface line, Microsoft controls the hardware and the software, right? Will send all of this out via Windows Update. You can also apply Windows updates and get updates to the DBX. So since there needed to be an update to the DBX this August, Microsoft did push out through Windows Update and allow people to apply that manually, a update for the DBX, and documented that in KB 501-2170. Now, if you plug it into Google, what you're going to find is a lot of articles saying that this update failed. And I'm not knocking Microsoft. I mean, they have a hard job, but there are some issues with that. Again, some of the advice is to make sure that your BIOS, UEFI BIOS, is up to date before you apply this KB. And you do this with caution, right? Don't roll this out to all, 100,000 Windows computers in your environment without testing first. So there's actually two things that it triggered in this update. Is it failed with a very specific error that you can see there. And also in some cases, it triggered a BitLocker recovery key. I believe because some of those core components in UEFI that support secure boot have changed, which then triggered the changes in BitLocker, which forced a recovery mode for BitLocker. And you don't want, the last thing you want, we've talked about this in our podcast, right, is 20,000 computers in BitLocker recovery and all those users calling the help desk all at once. That would be bad. So make sure you test this. Any questions on secure boot, DBX updates before we move on?
We had a couple come in really early in the presentation. So the first one was, can you use WSL?
I believe so. I am not the foremost expert on Windows Update or Microsoft updates, but these updates, especially ones for like Surface Pro laptops, for example, and these KBs, I believe can be pushed out through like whatever patching system that you have. These are, standard Microsoft Update and Windows Update patches that come out.
And one more came in from Tony. It says UEFI is turning out, like other things, to be not as secure as it was once claimed. What is the solution to isolate UEFI from attack?
Yeah, that's like a whole other presentation in and of itself. There's a lot more. It's a great question, Tony, right? There's obviously a lot more happening in UEFI other than being responsible for the major components within secure boot. Specifically to secure boot, there's a lot of non-technical issues, right? Like I think of it as the Spider-Man meme, right? Where you've got all the copies of Spider-Man and they're all pointing at each other. That tends to be how I think of when we have an issue like this, because is it the responsibility of UEFI to make sure they push out a DBX update and make it publicly available? Well, yes, it's Microsoft's responsibility, not only in their own ecosystem, but also to administer the third-party CA and make sure that that process is secure. And one improvement, Tony, to speak directly to your question, is I'll actually be covering on tonight's Paul Security Weekly podcast. Microsoft has changed some of its processes for validating software. Now, I believe it's a direct result as from the research from Mickey and Jesse and others in the community that have pointed out when there's flaws in software, we have to, do all of these things. Everyone has to update the DBX. These updates could break things. So Microsoft has put some further restrictions and recommendations for, like, when you submit software to Microsoft, it must have these extra security things, or we're not going to approve it as software that can be used in the secure boot process. So I think there are some, Microsoft is learning, but we all have to work together as well. It's a great question.
Here's another one from Nicholas. If a hash is in both DB and DBX, which one wins?
That's a good question. And I don't remember which one gets checked first. Let me get back to on that one. That's a good question for our researchers.
Okay, and let's take one more here and then we'll move on. It says, how do you check secure boot enabled or not in embedded and IoT devices, Internet of Things devices?
Yeah, that's a good question. If they run Linux and you can install those utilities, you could check for those. Other than that, you're going to have to go into your BIOS or the equivalent in those devices and check to see if it's enabled or not. So yeah, and if you want more information about that, I can, in specific embedded systems, I can do some digging on that one.
Great, and these are great questions, but Paul, I think we're ready to move on to the next section.
Absolutely. Let's talk about Intel ME. If you wanted a computer inside your computer, you got one. If you bought an Intel computer, for the most part, after 2006. And this is more firmware that needs to be updated. And I always do think of this exhibit meme. Like, I liked firmware updates so much, I put a firmware update, your firmware update. I liked computers so much, I put a computer inside your computer. And many of it, I mean, this has been evangelized quite a bit. I believe there's been a lot of concern, especially from the open source community, about the existence of Intel ME. And due to a lot of the things I outlined on this slide, right? Like the quick rundown, we could spend an entire presentation talking about Intel ME. But again, introduced in 2006, likely if you have an Intel-based computer, you have Intel ME in some capacity, and there has been some significant architecture changes over the years since 2006. Specifically, the microprocessor has changed from an ARC processor to a Quark x86 based processor at some juncture. In my blog post, I kind of lay out a little timetable for you so you can see exactly when these changes were made. It runs on a separate CPU and has its own SRAM with its own microkernel inside of your computer. It does store, for storage, use the SPI flash that it shares with the BIOS and other components. I'll talk a little bit about that more at the end. It introduces a new concept, which is not traditionally how Intel defines the processor rings or the operating system defines the rings of access. Ring -3 was kind of this concept or notion that we had to come up with to describe the level of access that something like Intel ME has on your computer. It has direct access to all of the components directly, independent of the operating system. In most cases, it cannot be completely removed or disabled. Some functionality is required in order for your computer to boot correctly. For a period of time, Intel, I believe, has not supported or kind of decommissioned the concept of an anti-theft mechanism built into Intel ME's structure. When it was in there, if you disabled Intel ME on your laptop, after 30 minutes, the anti-theft would kick in and your laptop would turn off. There are a lot of resources that I link to about Intel ME, and I have a full history of vulnerabilities and lots of resources in the link at the bottom of this slide if you want to dig in for more information. Now, some manufacturers, such as Apple and System 76, have their own arrangement, if you will, with Intel and have reduced the functionality of Intel ME. It still exists even in Intel-based Apple systems. It does not exist in, obviously they're not using Intel chips in M1 and M2, so it does not exist there. But for Apple Intel systems, it does exist with greatly reduced functionality. The same case with System 76, who makes Linux laptops. It's important to note that the active management technology, or AMT, is a feature set within ME. So every computer gets, conceivably, I don't say every, but for the most part, Intel-based computers get some form of Intel ME. Usually one's branded vPro, or a lot on the server side as well, will get the feature set that we call AMT, which allows remote access over the network. So that's the big distinction there. Security researchers have found quite a few issues with Intel ME and AMT independently over time. There's a lot of great research that has come out. All of the research that I could find, I've documented in my blog post that's linked to at the bottom of this slide. There's been several Black Hat presentations. It dates back to, I believe I dated it back to 2009. Introducing ring -3 rootkits was some of the first research I could find that has referenced that from Invisible Things Labs. So there are vulnerabilities in it that have been highlighted by researchers. One of those was dubbed Silent Bob is Silent, which was an authentication bypass in AMT. So part of ME, but specifically the AMT feature set. It was discovered in 2017, and Intel released a security advisory 00075 and released a tool to check specifically for this vulnerability. So if you have a slightly older PC, obviously this was discovered and fixed in 2017. So if your PC is slightly older, you can download this utility for free from Intel and run it on your Linux-based system, and it will check to see if your system is vulnerable or not to a vulnerability that was dubbed Silent Bob is silent. And so you can run that. I ran that on my systems. My system was not vulnerable, but that's a freely available tool from Intel to check specifically for this vulnerability. There's also, if you're wondering, like, do I have a computer with AMT? Like, if I have Intel processor after 2006, yes, I probably have Intel ME, but do I have the Intel AMT feature set? I believe it's Matthew Garrett. Yes, Matthew Garrett authored a tool that he makes freely available on GitHub to check for the active management technology, and you can run it. Now, if it can't connect to the management engine on your system, it's going to report back. It probably means you don't have AMT, because I couldn't communicate with the Intel ME on your system. There's a number of different reasons for that. I was chatting with someone on Discord, helping them through this process. So if you run this and you get this error, feel free to reach out. I'm happy to help. Also, it can be used, chipsec, which is a project that many of our founders and some of our employees are part of. In fact, we still contribute back to the open source project called chipsec that is also co-authored by Intel as well. It is an open source suite that runs on Linux, Mac, and Windows for enumerating issues and enumerating the firmware inside of your system. Chipsec has one module that deals with Intel ME, and that is to check for Intel's manufacturing mode. In manufacturing mode, and there's a link to the original research that talks about manufacturing mode. In manufacturing mode, there's essentially some switches and or fuses that must be set by the manufacturer to close off Intel ME's systems so that it can't be tampered with after the fact. If manufacturing mode is left untampered, it can lead to vulnerabilities. Again, they are all explained in that research. Essentially, if you have Intel ME and it's in manufacturing mode, you will likely have some serious vulnerabilities that need to be addressed on your system. And one of the ways to discover that is to install chipsec. So this screen is how you install chipsec. In fact, I just referenced this slide yesterday when I wanted to install chipsec on some newer systems that I had. And so you can see how to install it here. Installed great on the Linux systems that I have. Keep in mind, if you have secure boot enabled, it will not let you load the kernel module associated with that. And you have to take some extra steps to get that enabled. So if you run the module ME manufacturing mode, you can see it interrogates Intel ME and will tell you whether or not ME is in manufacturing mode or not. Also, Core Boot is an open source UEFI BIOS, if you will. And inside of the Core Boot process, they have an open source tool called Intel ME tool. Intel ME tool can be used to also query the Intel ME firmware on your system. And doesn't necessarily tell you things like, vulnerability for manufacturing mode, but gives you your firmware version, which I find really helpful to know what version of Intel ME you have installed on your system, so that, maybe then you can go to your hardware manufacturer and go, hey, is there an update for it? And if there's not, maybe ask your manufacturer for an update for it. So it will report using the -M flag, the firmware version for Intel ME. And again, freely available open source tool. It's got, some other options in there as well. This finally culminates with a tool that is available directly from Intel. It is freely available for a download. You can use the link on the slide to download it, install it, and run it on your system using the commands at the top of this slide. It will interrogate your system, and it will give you the version number of your Intel Converged Security and Management Engine, as they call it now, and also give you a risk assessment. Now, the risk assessment isn't terribly detailed. However, they do tell you if it's vulnerable to something or not. So it's kind of like it tells you vulnerable or not necessarily any more in-depth information other than that. It does run fairly reliably, I've found. Sometimes Intel ME tool from the Core Boot project and some of the other tools that I've mentioned don't compile right. You've got dependency issues, depends on the kernel version, things like that. This tool from Intel does run pretty well in my experience. Okay, again, the advice is to update your firmware. Now, you can go in and start mucking with Intel ME on your own. However, in most cases, your hardware manufacturer, ASUS, MSI, whoever is the hardware manufacturer of your computer, has made customizations to UEFI, to Intel ME, and therefore, if you try and apply your own update to it or mess with it in any other way, you could cause harm to your system. So my advice for Intel ME, and there is an open source tool called ME Cleaner. I cover it in my blog post. My advice is to, if you have Intel ME, make sure you update it in accordance with your hardware manufacturer recommendations. And update your firmware. And again, make sure you update your BIOS before you update your Intel ME system. Okay, protecting system firmware storage. On your computer, there is what we call the SPI flash system. It's actually a controller and a storage device that you interface with. Some of the tools that I mentioned, such as chipsec, will allow you to interrogate and interface with the SPI flash that is on inside your computer, which stores some of the firmware that is on your system, including your BIOS. So your UEFI BIOS is stored on your SPI flash. Intel Management Engine, as I mentioned, also has storage area on a storage region, I should say, on the SPI flash. Sometimes your gigabit Ethernet controller, your EC firmware can also be stored on the system SPI flash as well. And there are multiple mechanisms to control writing to your SPI flash. So this gets really complicated because there's multiple different ways to interface with the SPI flash and the SPI flash controller, in addition to multiple ways to protect the various regions, such that an attacker, as that happened with Trick Boot, will go in and say, hey, can I write without any exploit or vulnerability, just because of poor permissions, can I write to the SPI flash and add a module or replace something in UEFI so that I can install a bootkit that would then hook your bootloader and ultimately your kernel and operating system, for example. So there are multiple ways to do this. systems can require that system management mode, your system be in system management mode before allowing SPY flash writes. Now, there are also vulnerabilities associated with that process as well. There's actually call it a race condition that exists where you can write to the SPY flash before the checking is in place, but the SPY flash is writable for a period of time. That's documented, and also linked to more information about that in the link at the bottom of this page. This is also the subject of the third part of my firmware realizations post, where I'll cover this vulnerability and more information about write protection for your SPY flash. So there are BIOS control registers that can be enabled that says you can only write to the SPY flash when you're executing code in system management mode as a protection mechanism. So you have to be in SMM mode to do that. You can see the first region of the SPY flash is the flash descriptor region. The flash descriptor region basically defines how the SPY flash is laid out. So the offsets that says your UEFI has this region, Intel's management engine has this region, are defined in the flash descriptor region. So almost similar to the way a file system would describe how a file system table was laid out. The flash descriptor region also contains rules as to who and how writes happen to the rest of the SPY flash chip. So should this region be writable by this, and in what mechanism? So there are some rules that govern writing to the SPY flash in the flash descriptor region. So again, multiple ways to protect your SPY flash on your computer such that attackers can't install software of their choosing or backdoor or hook various components that live on the SPY flash. So you can check for this using chipsec. So we covered how to install chipsec, and if you run the module BIOS_WP or BIOS write protections, it will do chipsec will do an evaluation and determine if those BIOS regions are protected. So in this case, it's talking about the SMM-based write protection mechanism. So this computer basically BIOS lock enable or BIOS WE write enabled is set to 0, which means it doesn't have that protection that says in SMM mode is the only time you can write to your SPY flash. So that's what this vulnerability report is describing. So that's one module within chipsec. The other module that you can run requires that you dump your SPY flash to a file first and then execute the module against that dumped flash. So what I'm setting up here is I want to check if the flash descriptor is writable or not. So as I described, the flash descriptor region contains rules that govern who and what can write to the SPY flash. If, as an attacker, I can write to the flash descriptor region, then I can rewrite the rules. It's kind of like leaving your firewall completely open and anyone can log in and change the rules of your firewall. So I'm going to check for that condition on the system using chipsec. So the first thing I'm going to do is I'm going to dump my SPY flash to a file called fd.bin using the chipsec command up above. Then I'm going to run the SPY descriptor, SPYDESK module in chipsec. So I'm going to use chipsec util SPYDESK against my dumped SPY flash file. And what this is telling me right here is that there are 3 regions. So I've cropped the output. There's more verbose output, but I've cropped just this section to show the flash regions. So I've got a flash descriptor region, I've got a BIOS region, and I have an Intel ME region on this particular computer. This computer was not a laptop, so it didn't surprise me that I didn't have a gigabit Ethernet region, and I didn't have an that I didn't have an EC firmware region because that's laptop specific. It kind of did surprise me that I must not have a gigabit Ethernet adapter that would store stuff on the SPY flash. So I've got 3 regions, and master read-write access to those flash regions are read-writable. So in this case, there will be a vulnerability thrown. I don't know if I did that in chipsec, but definitely in our product, right? There'll be a vulnerability flagged that says, hey, your flash descriptor region is read-writable, meaning that attackers could rewrite the rules on there that govern writing to the SPY flash. So that's how you run that module. And again, you can, as a user, start changing some of these variables within your BIOS. In fact, the latest update to the Linux Vendor Firmware Service allows you as a user within Linux to interface with your BIOS and make changes to different configurations within your BIOS through the command line utility in LVFS. LVFS also, in its most recent version, which was released the other day, has a facility where you can do this automatically. Sorry, things popping on my screen. You can do this automatically as your system boots up, execute a script that is then setting these particular BIOS changes. So I don't know if I necessarily recommend that. That definitely has the potential to break things. Again, the advice here is to update your firmware. If the hardware manufacturer has shipped you a computer with a BIOS that has these insecure settings, hopefully they've been notified of that. They can release a new BIOS firmware update that will then correct these settings. And I'd like that to come from the actual hardware manufacturer in these cases, because it's somewhat less resilient, right? More resilient to bricking your computer, which is the worst case here. So again, the advice to deal with some of these issues, yes, you can go and start marking manually, but I like to apply the firmware updates from the hardware manufacturer. Really quick before we get into some more questions, some of the ways that I stumbled across these issues and started then digging into some open source tools to enumerate these issues and this particular types of firmware was I was running the Eclypsium product. So I just want to show you a few screenshots of what kind of led me down this path as I started using Eclypsium's product. It told me that I had in my device details, this is my BIOS version and firmware release date. So it told me that particular information right there in the web interface, and then it told me that my DBX database was out of date. Right, so if you deployed this across all of your systems, right, you would get an alert that says this is out of date. Now, Eclypsium's research team and product teams maintain a list of the latest DBX updates across all major platforms. So, our software is running on your systems and it's flagging a DBX update. It's because on the back end, we're paying attention to all the various DBX updates. You don't have to manually go discover that. It's all coming from within our product. And we have, researchers that are focused on making sure that we have the latest updates in the DBX and things of that nature. And once I did apply the DBX update, I could verify with the product that it was up to date. In the previous example, I could go through the path of looking at LVFS and making sure that I was, in fact, running the latest version of the DBX. When I run our product, it says my risk status and integrity status has passed. My DBX is now up to date. And if you dig into our configuration settings, it says the analysis is okay on our DBX default configuration item. So I then verified that my DBX was up to date. When a system has Intel ME and AMT, we provide a whole host of, lots of information about Intel ME and AMT, including the AMT status. I described this in my blog post. So you probably have Intel ME, you may have AMT, but if you have AMT features enabled, those can be in any number of states. So it can be disabled, it can be provisioned, not provisioned, and fully provisioned. There's like 4 different states. I cover that in the blog post that I linked to previously of what those states are. So the product will actually give you the state and the AMT version number and a lot of different information about ME and AMT. Also, as I was running some of these open source tools, it kind of told me that I was vulnerable, but not exactly what I was vulnerable to, or I could go to a specific vulnerability and test for just that. one of the things that I liked when I discovered using the product that, oh my God, I have Intel ME on my system. I'm like, that's weird. I never saw any way to update that. But it tells you the exact CVE numbers and list them by severity of exactly what you're vulnerable to for Intel ME. So I thought that was a nice kind of breakdown, is that if I'm managing systems and I'm trying to make the decision, should I push out an update for Intel ME to all of my systems? What am I fixing? Am I fixing a really low severity vulnerability, or are there high severity vulnerabilities? And which of my systems have high severity vulnerabilities and which ones have lower severity, and help me kind of manage how I should push this out. So I think that open source tools are great for you as an individual to look at your systems and evaluate the state of firmware security and the state of the firmware installed on your systems. That gives you immediate access to tools and information that you can take to your team, that you can take to your management team and go, hey, we've got a bunch of systems out here, and like Intel ME is out of date on a bunch of these, and like I ran these tools and it's shown that they're really vulnerable. And kind of use it as a proving grounds to say, maybe we want to look into better ways in which to enumerate all of this firmware in our systems and make sure that it's up to date. So that's typically how I recommend people use open source tools. Obviously, if you've got one computer that you're responsible for, great, you can use open source tools to enumerate that and do some of the investigations to keep your firmware up to date, to keep it better protected from attackers. And that concludes the presentation. 4 minutes for questions.
Thanks, Paul. A couple questions came in, and one we might need a little clarification on. Nicholas put this in during the Intel ME section. Does that tool connect over the network or through some internal interface on the host? I know you were covering a few different tools, so I'm not entirely sure.
Yeah, all of the tools, open source tools, will connect locally on your host to the device. Chipsec stands out as it will load a kernel module, and inside of that kernel module is a device driver that will interface with the lower level devices, such as the SPI controller on your system. And it needs to be a kernel module device driver, in order to do that. So it does not, to my knowledge, reach out to the internet to do all of that. It's local.
And just to clarify, Nicholas did respond with Matthew Garrett's tool.
Oh, Matthew Garrett's tool, I believe, is also a local tool to check for AMT.
Tyler came in with, are there products or strategies for updating firmware when the manufacturer does not provide updates?
That's a great question. And I get this question a lot, and I think about it a lot. And it irks me that you could be in the situation where, using the techniques I described today, discover that you are vulnerable and that a hardware manufacturer has not released an update for it. I'm hopeful that open source technologies can deal with this, that you could, in some circumstances, perhaps install an open source firmware. Coreboot is open source EFI firmware. If your device is supported, you could install that, and hopefully the Coreboot project, for example, could continue to support your hardware for an extended period of time beyond when the hardware manufacturer has done that, right? But other than that, I don't have great solutions other than compelling the hardware manufacturers to push out those updates. But as we know, hardware manufacturers tend to have cutoff dates when they're not supporting that device. They're not supporting firmware updates on that device. Apple does that. In fact, there was a great piece of research, an article that talks about the length of time that Apple supports particular hardware and firmware software and firmware updates for particular hardware, and how if you're updating to the latest version of macOS and your hardware is older and runs older firmware, Apple may not have renewed their licensing agreement to keep that firmware up to date. And so therefore, they're not going to provide the latest operating system on that laptop because it has hardware that runs firmware that Apple's like, yeah, that's not worth making work with our operating system and renewing our contracts for licensing agreements or what have you. So that's some of why it happens.
I am guessing Ian Oliver completely agrees, since one of his comments was manufacturer transparency about what they're doing is sorely
Yeah,
lacking.
yeah,
And I know you had a long comment on here, but I'm going to address one of the questions that came in right after.
sure.
Patrick said, his device manufacturer is smart enough to suspend BitLocker before a UEFI firmware update. Do you know why Microsoft does not suspend its own disk encryption when it pushes a DBX revocation list update normally?
Yeah, I mean, unless they're doing that to prevent attacks, right? Unless they're going, well, what if an attacker were to modify that, we'd want to trigger BitLocker. But other than that, like I'm not sure why it did that. I'm also not certain that it happened on every single, computer running Windows. It seemed to be just pockets of users, and I'm still trying to understand what is unique about those pockets of users that triggered BitLocker recovery versus those that didn't, right? Is that a configuration? Is it a specific configuration in BitLocker that allows for that or not? I'm not certain. I'm not the world's foremost expert on BitLocker, but I can follow up if you like.
Great. Well, we are now at the top of the hour, and I want to thank everyone again for all their participation and the engagement during the webinar. Paul, great presentation. Thank you so much again for presenting. Just as a follow-up, I know it came in a couple times, but yes, we did record the webinar, and we are going to be sending a link out to it, as well as a link to the slides. And I will also include the links to the blog posts that Paul referenced, just so you can quickly link to those, but they are also linked in the presentation as well.
Thanks,
At this
Melissa.
time, we are all good, and we wish you all a wonderful rest of your day.
Thanks, everyone. Thanks, Melissa.
Thanks, everybody.